In this video, we are going to learn about how the word decibel has come from the sound of the decibel. I mean, from the measurement of the sound, how they have been applied to the electrical signals is what we are going to discuss. So before starting that, let's discuss about what is a gain is. So for instance, I'm having certain block. That block I'm named as A, and for that block it has two one input and one output. That input has given as 1 and the output is 10. So the gain of the block can be represented as 10. The gain is represented as the output, how much amount of output that we are getting to the input that we are giving. In this case, the output that we are giving is 10 and input is 1. So the gain of the system is 10. So let's take one clear-cut example in this case for a certain amount of power gain. So power gain is represented as output power to the input power. So for example, I have output power of 200 milliwatts and the input power I have given is 100 milliwatts. So the gain of this one is 20. So but if you want to represent for a longer scale, it would be really difficult to put this gain in terms of a linear scale. That's why we wanted to put in terms of a logarithmic scale, because logarithmic scale will give you a compressed signal representation. So that is what the fundamental thing has come, that is bell gain. So the bell gain is log to the base 10 of the ordinary value of the gain. So now let us consider about how this bell gain has come into picture. So G dash I am representing is a log 10 to the log gain to the base 10. So gain in this case is 20 to the base 10. So now we are writing it as the actual value that is coming is 1.301. Now you may wonder why that the people are representing in terms of log, and then sometimes it also see that it is multiplied with a 10 with multiplication of 10. So now let us see one particular example. I mean, this is all for just our own understanding purpose. The people has represented, there is no specific logic for it. For the natural tendency in increment or lateral tendency in decrement, how these things will happen, I'll just show you here. So now let us take, for example, I am taking on x-axis and y-axis. So on x-axis I'm taking a factor something like 1 2 3 4 5, and another axis I'm taking the gain. Say for example, for the factor of 1, the gain I'm measuring as G dash is equal to 10 into log 10 to the base 10. It will be obviously 0 dB, because log 1 to the base 10 is 0. When I'm keeping at 2, so it is the answer will be 3.01 dB. When I'm keeping at 4, the answer is 6.0 dB. Now you can see the natural incremental tendency phenomenon. When it is 1 to 2, it is from 0 to 3.01 dB, and 2 to 4 it is 6.02 dB, 4 to 8 it is 9.03 dB, and log 10 to the base 10 is 1, so it will become 10 dB. Now if I put in terms of small on x-axis the if I put the x-axis and the gain and dB, I'll see the factor on x-axis and the gain and dB on y-axis. We can clearly observe this very natural tendency phenomenon. When gain 1, so I'll start from with 1 and I'll make it double to 2, and then 2 to double 4, 4 to double 8, and so on. So when the gain is 1, it is 0 dB. When the gain is 2, it is 3.01 dB. When the gain is 4, it is 6.02 dB. When the gain is 8, it is 9.03 dB. Now if you see, 0 to 3 is 3 change, 3 to 6 is 3 change, 3 to 6 for every change here. So how things are happening, for every doubling the 3 dB is getting incremented. Now let us see what is happening when you go below the 1. So when you make it 1 into half, you will get minus 3.01 dB, and 0.5 half is 0.25, it is minus 6.02 dB, and 0.25 half is 0.125, it is minus 9.03 dB. So for 0.1 it is 10 dB. So if you see, for every change in the half, that is 50% of it, it is the dB changing by 3 dB. So that is how, if you see the complete scenario of increment and decrement, and if you put everything into a particular graph, you can observe that. So if I start with 0 and then 1, if I start with and then making double 2, making double 4, so at 1 it is 3 dB, at no, it is at 1 it is 0 dB, at 2 it is 3 dB, at 4 it is 6 dB, and at 8 again it is 9 dB. So now if you see, for every changing a factor of 2, if it is, then the value is getting multiplied. Now when you go below the point 1, for every change in half of this value, so minus 3 dB is getting reduced. At 0.5 it is minus 3, at 0.125 it is minus 6, and so on. So this is the reason why they have just multiplied with 10, and the answer is very simple. So at the factor of 1 it is crossing 0, and so on, it is very increasing 3 dB and so on, and it is having like this. So that's the reason why how it is. So let us take one simple example to calculate the gain, okay, in terms of power. So here, so I'm assuming there is an amplifier, and the amplifier has a power gain of 800 watts, okay, 800. Now if you wanted to know what is the decibel power gain of this particular amplifier, firstly we will write its formula, and this is mainly purpose of the computational, uh, you know the speed of the computation they wanted to increase just by having the numbers. That's the reason why they just multiplied with 10. Otherwise there is no much significance according to me. So now g dash is equal to 10 log to the g to the base 10. Now the gain is here 10 into log 800 to the base 10. So now this 800, how do I write? So whatever the known values that I have, from there I'll write 800. 800 can be written as 2 into 2 into 8 into 100 first I can write, and 8 is written as 2 into 2 into 2, and so in 10 into 10. When the multiplication, if there are any multiplication or division, when you put into log it will become addition. So for 2 is 3 dB, 2 is 3 dB, 2 is 3 dB, and 10 is 10 dB, 10 dB. So the overall answer will get 29. You just cross check, you would have got 29.303 dB. So that is reason why they are just putting 10 into log g to the base 10.